So 40,000 kilogram, plus that's the mass, moving at this speed, v, along a straight track. Straight, say there's M2, M1, M2, and couples with it, that means joins. What will the speed of the it doesn't, it's not very clear that they're going in opposite directions, but let's see. What's that? Oh, yes, right. Right. Thank you for that. Okay, so the only thing with momentum is the freight track, and then they join. This is pretty straightforward, isn't it? You've got 40,000 kilograms times 5.0 meters per second. You got to get this one every time. Then they join to become 70,000 kilograms with the new velocity. Multiply these two numbers and divide by 70,000. I think our smallest number of significant digits is 2. Bring it down to 2. Did you get 2.9 meters per second? Yeah, that's kind of basic, right? That's an inelastic collision because they join. If I stray too far from the monitor, get me back there because I'm recording this for someone who's out. And if you move even a little bit away, you really can't hear the teacher. Good? 2.9 meters per second? Okay. 2 balls equal mass. Speed. Collide head on. Find the velocity of each after the impact. If they have an inelastic collision, that means they stick together. So, you've got these 2 balls. Oops. You don't know their mass, so we just call them M. And they're going in opposite directions. 3.0 meters per second. But the other one must be negative. And then they combine. What's their mass after they combine? If it's inelastic, what's the mass? We have a single object with a single velocity. So it's not good over yet. Oh, well, actually, the answer is 0. But wait, we're just saying that if they collide and connect, because one thing, what's the mass of that one thing, Isabella? If they two M's collide and become one thing, what's the mass of the one thing? 2M, right? But by the way, your answer is right. But okay. So this adds up to 0. The total momentum before is 0. The total momentum after is 0. Okay.
Why would you leave the V 0?
By the way, this is V prime. What do you mean by leave the V?
Like, why did you write it there?
What did I write? This? What shouldn't I have written?
Wouldn't the V go away because they're both moving at the same speed? They cancel out.
Yeah. Look, because 3M plus negative 3M. I was just working it out. Just working out the math, and maybe it was so super obvious to you that each one had an equal but opposite momentum. So the total momentum before is 0. They add and join, they become 2M, and what's their new velocity? Yeah, 0. Did I just do too much because it's too obvious to you? Yeah. Well, because it's an inelastic collision, they stick and join. Inelastic collision, they collide and they become one thing. That's what inelastic collision, they stick. And so the M and M now become 2M. Maybe like the Velcro and stuff like that. Okay? That's what inelastic collision, they stick and collide. Or like in a car accident. One guy hits another guy and they just move together as one thing. So, yeah, that's the physics proof that she's right, the velocity is 0. Okay? Let's simplify. Oh, now they have a perfectly elastic collision. No energy is lost in the collision. We're not up to that just yet. We'll do energy. KE is conserved. What do you think? I bet you know the answer, though. You probably know the answer. Yeah, they're both neither of them lose their kinetic energy. They'll be they'll just bounce over 3 and 3. Doesn't really happen, but things come close to that. Oh, this one's a beauty. This one's a beauty. Let's slow down on this one, because the other ones are kind of obvious. 4 girls, each one of them 50 kilograms. They're sitting on a boat. The boat's at rest. They're at rest. They simultaneously dive horizontally in the same direction at 2.5 meters per second on the same side of the boat. What's the boat going to do? When the 4 girls dive this way, what's the boat going to do? Because Newton said so, it's going to go this way, action, action, reaction. Girls apply force on boat, boat applies force on girl, an action-reaction pair. The empty boat has the speed. What's the mass of the empty boat? All right, girls, what's the total momentum before? Well, they said the boat was at rest, the girls at rest. The total momentum before, obviously, is what? 0, yeah. Total momentum before, total. This is all coming back to you. By the way, when you do an AP, don't write mom, but I'll write it over here to be quick. Total momentum before equals 0. Everything's at rest. But why? All at rest. Boats at rest, the girls at rest. And then the girls, I'm not going to, why don't I just say that 4 girls are 200? Tell me if this makes sense to you. They all have the same mass, 4 girls, and they all have the same velocity. So is that okay if I do that? Do you get that? I just rather do 50 times 2.5, 50 times 2.5, 50. I just brought them all together. Does that make that too much for you? All 4 girls with the same velocity, plus this boat, mass of the boat, times point. What is it? 500? Yeah, 500. Bring it on this side. Oops. My bad. What did I do wrong here? How could I get a negative mass for? How could I get a negative? I did something wrong, did you? If I call this positive, I have to call the other direction negative, don't I? Yeah.
Isn't the mass of the boat and speed axis in the left side?
Say that again?
Isn't the, like, the mass of the boat times speed afterwards supposed to be on the left side?
Well, the total momentum before is 0. The girls would rest, the boat is at rest, equals the total momentum after. After each, the boat has a momentum going this way. And the girls have, yeah. Yeah, sorry about that, girl. I messed up, didn't I? If I'm going to call the girls 2.5 positive, I have to call the. So. And what is it, 5,000? You divide both sides by 0. Yeah, or, okay, how many, I guess, how do you show 5,000? Oh, wait a second, no, the velocity is, this is one significant digit, yeah.
Okay, find the 0.1 is negative, but why is it
Say that again?
like, I get why the boat velocity is negative, like, why is the girl velocity negative, or the girl mass negative?
Oh, it's not negative. What I did is I subtracted the girl's momentum, put it on the other side.
Okay.
Yeah. So that's how it became negative. I set it on the other side of the equal sign. Now the negatives will cancel. Now we get 5,000. But how do I write that with one significant digit? Just like this. Is your sheet? Yeah, your sheet is 0.1, so we can write it like that. Okay. What is the change in mechanical energy of the system? Cross that. I went out up to that just yet. So that's very interesting. Okay, now even more interesting is 6. Why don't you read and think about that? Underline, think about that one before I jump in. Why don't you think it's an interesting and unusual question? It really brings us to the next level. So you underline, I'll underline, we'll meet. Think about that. Moving eastward, frictionless section, 3 meters per second. Second truck, bigger map. Oh, moving north, same intersection. They collide and stick together. It's inelastic. So why is this a conservation of momentum question? Collision, interaction. What's unusual? What have we never seen up to this point? Yes?
Well, it's not a straight collision, it's like.
Yeah, oh my God, these are, things just going the X direction, the Y direction, so easy. Yeah.
Is it like the question we did a while ago with the plane, like the wind makes it go faster?
These vectors are not going in the same direction, so the vector mathematics are not super simple. You don't want to bother with vectors. But when they're going perpendicular, you should be always thinking about what, vectors that are perpendicular. We can add them, but it's a little tricky, not much. How do we add two? Two vectors are 90. You have to look at that. So total momentum, let's do the total momentum before. How do we find the total momentum before? Not super easy. Total momentum before. Well, it's a little more tricky. We have to use the PYTH because they're 90 degrees to each other. So I have to use the P total equals the square root of the truck, 1,000, going east, 3 meters per second. That's really too significant. But we're going to square that whole thing, put little brackets. It's the square root of each one of them squared plus the second truck, 8,000, multiplied by 2.0 meters per second. That whole momentum gets squared. So what's this? I guess it's just the square root of 12,000 plus 12,000 squared plus 16,000 squared. That's how I find the total momentum before, when the 90 degrees. The rules for vector addition is when the 90 degrees is the side you're doing. So work that out for me. That just gives us the total momentum before. And what does that turn out to be? Yes?
20,000.
Okay, 20,000 girls, we're all good on that? So the total momentum before is 20,000? That's 20,000 kilogram meters per second. That's the total momentum before. Equals the total momentum after. So if they're inelastic, there's a single body with one mass, one velocity, right? What would that be on the Schneider? What would the new mass be? You got a 4,000 kilogram truck and an 8,000 kilogram truck. They smash it. You've probably seen a car accident. It actually become one body moving across the road. What's the mass of the single body? 12,000. So now it's very easy. Times their new velocity. And notice they said speed, and I like that because all I need is the magnitude but not the direction. That's great. When we're done, let's circle that word speed. Means we don't need direction, right? Yeah.
Is there a way to find direction? I know we don't.
Yeah. We're gonna get to that. That's the next level. We're not gonna get up to there. Just it's written. There is a way to find the direction. Pretty much. It's good. We're not there just yet. What's that? Yeah, I mean, we gotta get into that. It's just the next level. We're not gonna get here yet. What does that turn to be?
Sorry, what were you 12,000?
Oh, it's an inelastic collision, 8,000 plus 4,000, the two trucks combined. Because, so then you divide both sides by 12,000, you get 1.7 meters per second with two significant digits. What is the change in kinetic energy? We're not doing that till we do energy. Name the two places where the energy went. Well, in the collision, there's a sound, and listen, we're not there, but we're right, a sound. One car does work on the other. This is stuff we're not into yet. We'll get into it. Lots of energy is transferred into the work done on the dancing the car and all that. That's all done. Let's get out our next handout, which looks like I think it looks like that. Oh, let me talk. Thank you. Let me talk about the quiz. The quiz is the homework. It's not posted. It'll be posted at the end of school. There'll be a code that you'll get to copy paste the code, and it'll give you entry into the online quiz. Okay.
That's on.
Hmm?
It's on.
It is not done. Yeah.
Is it all what we're doing just now?
Oh, no, it's not this new stuff. It's actually the basics. It's easy. It's pre-conservation. It's impulse, force, and time. It's much simpler stuff. I mean, it's not that super simple, but it's not this complicated. It's no conservation of momentum. It's force and time is impulse. If you want to change the momentum, it's not just about force, it's about force and time. You know, basic stuff. So, yeah.
Is it due tomorrow or?
Do tonight. Oh, thank you. Do tonight. I'm going to close it down before I go to bed. Do it. I'll be at 10:30 is my bedtime.
That's fine.
Is that too early?
Can you like close it? Is there
Can you
a-
explain as well? You can like set it next morning, like before home.
Maybe when I wake up.
I don't know.
When they get to bed, we're all. Go to bed very late, like 11:30. You know what, I turn up my alarm on vacation, I woke up late today, but I made it, I'm so glad. All right, you got this Civil War, you ever see those, I think one of the greatest, examples of action reaction and conservation momentum, you ever see those old Civil War cannons when they shoot, the cannon goes back? The cannonball goes this way, and the cannonball goes back, and they're made at a tremendous amount of mass. Makes sense, right? Imagine, they probably learned over time, we better make this cannon a lot of mass, or else we shoot the cannonball, it'll wipe out our side. You know, as the thing recoils, you have to have the inertia to handle that cannonball. And we've all, I think we've all seen cannons, and there's a tremendous amount of mass. What's the physics of that? If you're going to shoot a cannonball this way, you know you're going to get a recoil. Why? Because before the cannonball is fired, what's the total momentum before? So how much? Before the cannon is fired, what's the momentum of the cannon, the gunpowder, and the zero? So we know we're going to get an action reaction. The cannonball will go very fast, and the cannonball goes so fast, which is good because it doesn't wipe out our side. You fire the cannon, it will roll back, it's got wheels on it. But sometimes they used to have wheels on it, it would recoil backwards, and I think then they started to develop cannons that could go back, like if you're on a boat, they would actually go back themselves rather than have wheels on them. But that's called recoil. Did I use that word recoil yet? You ever see a movie with a gun? You always know the gun back, right? That's the recoil. Because the force that the gun exerts on the bullet is the bullet's force on the gun and the shooter. That's why, shooters crouch, because they know they're going to get a reaction. It's not just the gun that takes the reaction, it's the whole, it's like, it's a very powerful gun. I know what you're talking about. Having shot a gun since he shot the BB gun. John Cushing was 12 years old, 13 years old. But that had a little recoil. It's the last gun I shot, 13 years old. So the action and the reaction, and if you, I would imagine, I don't know a lot about guns. I once heard that you have to, for super powerful guns, I could be wrong, you can't just sell it to everybody. have to have the inertia to handle the recoil. So it's an amazingly powerful gun. They might, if you're 100 pounds or 60 pounds, they might say, is that true? Okay, but you don't want to say, you shoot guns?
Yeah, I want to.
So you have the mass to handle the recoil. I always tell the story, my father was a cop before he started his own business, but he was a cop, and he said, the cop, he personally said, it was a horrible shot. I'm so lucky I never had to use my gun because it did a thing. But he said the detectives would go upstate, all of them would go upstate, and they would practice shooting. And he said that, we would get instructions on how to do it. And then inevitably, 100 cops went upstate, and you're gonna know the answers. And some guys just did not listen. Probably those days it was just guys. Where do you put the butt of the rifle? Where don't you put it?
Where don't you put it?
Yeah,
Your shoulder.
shoulder. And guess what? You say, certain percentage of cops were going to the local hospital because they had dislocated their shoulder. Because the shoulder should not take a recoil. You put it right here. Yeah. Put it right here, and if it's a super powerful gun, you probably brace with that recoil. The rifle's taking the recoil, but you are too. Your whole body. The bullet is very tiny. It's less mass. And so, yeah, he said people wouldn't listen, and they put it right here. And it had a little weak shoulder. Dislocate their shoulder. That's called recoil. So we watch a cannon shoot the cannon recoils. Big mass cannon recoils. It's got a lot of inertia, the resistance to a change in motion due to mass. That's why they designed as years went by, and realized to make these cannons have a tremendous amount of mass because the recoil would be too great and whoever was behind the cannon would be wiped out. So we've got this cannon, Civil War cannon, that's underlined. Let's do what we always do. Cannon is fired. It's got a tremendous mass, no surprise. And the cannonball, look at it's big, but it certainly doesn't have the mass of the cannon. And it goes at this tremendous speed. It's elevated at this angle, and the length of the barrel, which we never use, is 2.1. What is the recoil velocity of the cannon? What's the total momentum before, girls? It is, before the cannon is fired, the momentum of 0, because the cannon, everything's at rest. The cannon is at rest, the cannonball is at rest, the gunpowder is at rest. Then you've got this cannon. It has a momentum. But we don't know what it is, do we? Oops, then plus the cannonball. And it's got a velocity. We'll call that positive just because, well, whatever. Right? We'll call it positive. Right? And now it becomes a simple recoil problem. It's a math problem, right? Subtract 875. You could take this number and put it on the other side of the equation. You know your algebra, right? You know your algebra. You get a negative. What's a negative? Yeah. Well, it is, and when you solve it, you're going to find it is. If we bring this over, that'll be negative. You got a negative b. I called the b that I need positive, and it just has to be as an unknown. But check out, when this goes to the other side, you divide both sides, you're going to get a negative b. So an unknown doesn't have to be given a. And what is it? Negative 5 point. Let's see, how many seconds we did? This looks like 3. Negative 5.80 meters per second. But let's squeeze something in that's so critical for conceptual question, right? The momentum of the cannonball is, how does it compare to the momentum of the cannon? Momentum of the cannonball is equal but opposite the momentum of the cannon. That's what you should know when an object starts at rest. Momentum of the cannonball is equal but opposite of the momentum of the cannon. Doesn't that make sense? That's how they get up to zero. That's how they get up to zero. They have to be equal but opposite because if there's zero before, there's zero after. All right? If there's zero before, there's zero after. All right? Okay, equal but opposite. Zero total momentum before is zero, total momentum after is zero. How far does let's get rid of that one. That's quite a question. It's a kinematics question. But I really like the next one. What is the momentum? It's a good little review. And it shows you we never really leave a topic, unlike Regents physics. Regents physics. We never leave a topic because we're back to forget. Well, be careful with that. You know what? Something is zero at the peak. I keep calling the same people. What's the which one though? Isn't it just the y velocity? Be careful. At the peak, it can't be that everything's zero, right? Because how can it move forward? Vy is always zero, but Vx is not. So it's all Vx. Could you write that down? At the peak, it's all Vx. Remember that. It's all Vx, because all the Vy is down at the peak. So, how do I find the momentum at the peak? It's all Vx. I have to find what else do we know about horizontal velocity? Who remembers that? In this old topic, horizontal velocity is beautiful. Some of the critical things you have to know about projectile motion. So if I find the horizontal velocity at the beginning, I know the horizontal velocity. How do I do that? Oh, with trigonometry. Vx equals, what's that trig? I do have an angle. How do you find the horizontal, Olivia? Because we have an initial velocity, we have an angle. What's the trig on how to find x components? What's that trig function that always gives you x? Is it sine or cosine? Right. This is just a component question. So if I could find the Vx at the beginning, and Kim just told me, well, it doesn't change. Find the Vx in the beginning, you find the Vx at all times, and then you could do Px at peak. At the peak is just going to be m times Vx. Px at the peak, well, the momentum at the peak, it's all x. Okay, that's a good one, huh? That's kind of an AP one. So what does that turn out to be? A full, yeah?
Why is it V cosine?
Well, because if you've got this projection angle, could you give me that angle? What was that? Because x is the horizontal component and cosine is the horizontal, is what you use to find the horizontal component or something. Remember this? The cosine theta, because there's theta, right? The adjacent side. So girls, 4160 kilograms per second. 4160, okay? Because the Vx is 145 cosine 35. Vx is 145 cosine 35, 145 cosine 35. And so what you get is m, the mass of the cannonball is 335. G, and then we use V cosine theta. The initial V times cosine theta. And the answer is 4160 kilograms per second. What do you think about that? Takes you back. So let me summarize what I just did is, I said at the peak, don't make a mistake. Vy does equal 0, but Vx does not equal 0 at the peak. At the peak, it's all Vx. So I can find the Vx in the beginning. Kim said Vx doesn't change. The Vx in the beginning is equal to Vx at the peak. And there you go.
What was the answer?
The answer was 4160 kilogram meters per second without a decimal. 4160, did you get that? Now I believe, tell me if I'm wrong, we did before, but it's good to do it again. Tell me, am I wrong? Who's got a good memory? I think we did it next. I think we did it before, but we could do it again. So we've got a mass. We got this speed. Now, if you go from 20 to 22, a lot of people think, oh, it's a change of 2. It's not the change in velocity. It's not 2. Why? Read that and think about it. Why is it not 2? Yeah, there you go.
Because it's hit that.
Beautiful. Let's highlight that. So if I call this positive 2, which I could, then so VI is positive 20 meters per second. I have no choice because it goes straight back to call this negative. So this is a tremendous change in velocity, isn't it? A really big change. Think about the number line when you're young kid, you learn about the number line. That's a big change. That's a change of, well, VF minus VI, negative 22 meters per second, minus 20. So it's a big change of negative 42 meters per second. Now, why did I do that? Well, I wanted the impulse. Impulse is the combination of force and time, but that's not going to help me. But it also equals m delta v, and there you go. That's how I'll do it, impulse.
Freshmen and sophomores may leave.
Am I right? Did we do this right? Yes. Did you get positive, impulse delivered by the bat to the ball is negative 6.3 times 10 kilogram. Did you get negative 6.3 kilograms per second?